In this video, I will be talking about evaluating definite integrals. So now that we learned what definite integrals are, we're going to be able to evaluate them. And to be able to do that, we need some knowledge from our potential previous mathematical experience. And I'm going to list out some of those things. And then I'm going to list out some simple rules on the right hand side. So here, what we need to know is the sum I equals 1 to n could actually be calculated of I could actually be calculated as n times n plus 1 over 2. What this means is if you think of a sequence that looks like 1 plus 2 plus 3 plus 4 plus 5. So what this means is that it is basically the sum of I from 1 to 5 of I, right? So that could be represented as that. So what it's telling you is that calculate the sum of first 5 terms, which could be easily computed as 5 times 6 over 2, because it's n times n plus 1 over 2, which is going to be something like 15. So you can calculate any sequence, any summation using this formula. Second example is when we have squares. In other words, you have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. If you have an example like this, you can represent it as this using the summation notation from I equals 1 to 5, I squared. So it's from 1 to 5. So add up all the squares. To calculate that, we'll do n times n plus 1 times 2n plus 1 over 6. So n in this case is 5. N times 1, n plus 1 is 6. 2n plus 1 is 5 times 2 plus 1, which is 11, over 6. So this will give you 55. So the sum of 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared is basically 55. Here, the situation in which you're calculating the third degree, right? The cubes of numbers. So what this means is that 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. And this could be represented as sigma I from 1 to 5 I cubed. And then the way we calculate that is n times n plus 1 over 2 squared. So I'm going to do n times n plus 1, so 5 times 6 over 2 squared, which is 15 squared, which is going to be 225. Okay, so those are some of the things about sums that we need to know. Here on the right hand side, we have some simple rules. For instance, if you have sigma I equals 1 to n of c, you guys notice this guy doesn't have any I, right? So what this whole thing represents is basically adding c n many times. So like first term will have a c, second term will have a c, third term will have a c, all the way, because this was the first term, second term, third, all the way to the nth term. So this is basically adding c n many times. Because of that, we have n many c's. And that summation will be basically n times c. Okay? The second one, you guys notice we have the term a sub I. So it is going to be some term that we don't know, but we have a sequence going I equals 1 to n times c. So you guys notice it's multiplied by some constant number c. And so if we have situations like these, we can always take out the c and then say c times the integral ai. Okay? So you can always take out the sum, calculate this, and then multiply it by c. And then if we have two different terms such as a sub I plus b sub I, and if you're taking the sum of these terms, then you can split them into pieces, calculate a sub I first and then b sub I, and then add them up. Or subtract, right? It works for addition and subtraction. So those are some of the simple rules that we might need in the future. So what we're going to do next is I'm going to illustrate how to evaluate the Riemann sum for f of x equals x cubed minus 6x, taking the sample points to be the right endpoints and assuming the lower limit is 0, upper limit is 3, and n is 6. You guys notice n represents number of rectangles you're using to approximate the area. So a represents lower limit, b represents upper limit for the x points. Okay, so then we know that n is 6. So how could we find width? In other words, delta x. Because we know the whole interval goes from a to b, then we can subtract those to find that whole length and then divide by the number of rectangles, which is in this case 6. So we're going to say, let me write it this way, over n. So b is 3, a is 0, 6. So we will get 1 over 2. Okay, so based on this, then we can find the inputs or x's. So then it's gonna be, if we'll let x1, so we're gonna say x1 is basically a, which is 0, plus delta x. I'm gonna write it as that, a plus delta x. So in this case, a is 0, delta x is 1/2, so it's 0.5. Then we can do x2. To find x2, we're going to say a plus 2 delta x. Then this will be 0 plus 1, which is 1. Okay. x3 equals 3 delta x. So a plus 3 delta x will give you 1.5. x4 equals 4 delta x. So 0 plus 4 delta x is 2. And x5 equals, add another delta x, 2.5. So 5 delta x is x5. Again, these are my right endpoints. All the right end points for rectangles. Now I'm going to go ahead and compute the sum of the areas, right? This represents sum of the areas. So I'm going to say the first rectangle will have delta x as the width, and height is going to be f of x1. And then I'm going to continue writing delta x for the second rectangle, and then f of x2 plus delta x f of x3 plus delta x f of x4 plus delta x f of x5. And so we know that delta x is 1/2. So 1/2 times f of x1. We're gonna say we're gonna calculate f of x1 because x1 is 0.5. We previously found that right here. Plus 1 over 2 delta x again f of x2, which is 1, plus 1 over 2 f of 1.5 plus 1 over 2 f of 2 plus 1 over 2 f of 2.5. And because we know what the function looks like, function f of x is x cubed plus 6x, all of these heights for the rectangles, so f of 0.5, f of 1, we can easily calculate those. So when you calculate those, you will be getting a bunch of numbers. So I'm not going to do that calculation. What I'm going to say is just note here, note, you use f of x equals x cubed minus 6x to calculate each of these f values. And then overall, when you do it, you're going to be getting negative 3.9375. 9375. All right. So here you notice that the given function is actually not a positive function. So the approximation we found was negative, right? You guys notice the approximation is negative 3.93. And the reason for that is because we have more rectangles below the x-axis than above the x-axis. And you guys realize in this picture, because I was using the red endpoints, these are how the rectangles are formed, right endpoints. So first 4 rectangles are negative, and then the last 2 rectangles are positive. But because this whole thing is going to be a net area, I'm getting a negative area. So instead of 6 rectangles though, what if we use 40 rectangles? And then compute the sum again using the same procedure I did in the previous slide. Then we would get R approximately to be negative 6.39. You guys notice with the R, I'm sorry, this is not 6, this is 40. R sub 40. You guys noticed previously I did R of 6 and then I got something like negative 3.93. And you guys noticed this was not the best approximate because I did not use smaller rectangles. I only used 6 rectangles. But if I used 40, then I'll get a better estimate. As you can see in the diagram, I'm approximating area under the curve better. And as I increase my n's, so again, n is number of rectangles, I'm going to get better and better approximate. So if I have 500, 1,000, 5,000, I'm getting better approximates for the area. So what I'm going to do now is then, I'm going to compute the area with n many rectangles. In other words, I'm going to let n to go to infinity because I want a better approximate for the area under the curve. Because r equals 40 or n equals 40, n equals 6 doesn't give me the examples I did previously doesn't give me the best results. So because of that reason, I'm going to do n goes to infinity. So the way I'm going to do that is I'm going to take the limit of this Riemann sum. Okay. So again, this Riemann sum represents the total areas of rectangles. Okay. So this whole process seems to be a little bit chunky, but it's not too bad to follow. So what we're doing here is first we're going to rewrite the f of xi. So the way I'm going to do that is 3i over n. Part of the reason is that you guys notice delta x is always b over a over n. So because I'm saying that b is 3, a is 0, and I'm going to keep n as n many rectangles, right? And so for that reason, delta x is always 3 over n. And then the way I'm going to find each of xi's, let me write it this way. the way I'm going to find xi's is going to be always a plus I times delta x. So because a is 0, I is the general term, delta x is 3 over n, then xi is always 3i over n. So that's where we're going to plug that in. And you guys notice here we have delta x, which is 3 over n, which is what I just calculated. So rest is going to be simplification, you know, whatever you name it. F of 3i over n is basically we put this into the function. So you guys notice f of x is the given function we have is going to be x cubed minus 6x, I believe. So what I did here is that you calculate f of 3i over n. So you get 3i over n cubed minus 6 times 3i over n. Again, it's just calculating the function, evaluating it for 3i over n. And then what we did is I take out the 3 over n here because it's just a constant. So this is one of the rules that we learned earlier about the sums. So I just take out 3 over n. Inside, you basically do some simplifications. So you cube the 3, 27, cube the n, n cubed, I cubed, minus, put the 6 inside. So 16 or 18 over n times I. Next step here, we take out all the constants. So we basically split the summation. So split, and one of the rules that we learned earlier is if you add or subtract two different terms in a sum, you can split them. So as you can see, I split the first term and then the second term, and then you take out the constants because 3 over n is going to be distributed for each of these guys. So this one has 3 times 27 over n cubed, which is n to the 4th. And then this one has 3 over n times 18 over n, which is going to result in 54 over n squared. Now we simplify these sums so that they only have i's in them. You guys see? So what I cubed represents is basically finding the sum of cubes from 1 to n, and that could be calculated with n times n plus 1 over 2 squared, which is one of the formulas we see earlier in the slides. And we can do the similar thing for calculating I, because I from 1 to n represents adding all the numbers from 1 to n. So that is n times n plus 1 over 2. So you distribute these numbers, and then you get this. And then from there, you're going to realize that this parentheses goes I think goes to 1. And then the limit here also goes to 1. And then the whole thing becomes negative 6.75. So this, folks, is the exact value under the curve. Is the exact value under the curve. I'm not gonna hold you guys accountable for this kind of work, like this specific type of work, just so you know, but I want you guys to understand this whole process. Like what I did is I computed the area under the curve using n many rectangles, and then I'm gonna take the limit as n going to infinity. So now I'm gonna do one more example here. This example, we have integral from 2 to 5, x to the 4th dx. So I'm going to set up an expression for this integral as a limit of, as a sum of limits. Sorry, as a limit of sums. There's a typo here. Okay. So now first let's calculate delta x, which is the width of each rectangle. So that's always b minus a over n. So I know that b is 5, a is 2 over n. So we have 3 over n to be the width of each rectangles. And based on this, let's find xi's. So the way we're going to do that is xi equals a plus I times delta x. So a is 2, delta x is 3 over n. So we're going to say 2 plus 3i over n is always the general term for xi's. So this is equal to xi equal to xi. And so using the theorem that we previously learned relating definite integrals with the Riemann sums, so you may remember it looks like so the rule says from a to b f of x dx is the same thing as limit n going to infinity the sum I equals 1 to n of f of xi times delta x. So using this, in this particular example, I'm gonna say then integral, what was given is 2 to 5 of x to the 4th dx could be written as limit n going to infinity of the sum I from 2 to 5 oh wait, that is not true because we still have n many rectangles. We don't care about these boundaries because we know that we have n many rectangles. We have n many rectangles within 2 to 5. That's why we're going to have I equals 1 to n. And then we're going to say f of xi, like how we have here, times delta x. And then we're just going to replace those things. So it's going to be a limit n going infinity, again sum of the rectangles. So f of xi, in this case, we know what xi is, this guy. And so we know what f is, x to the 4th. So we're going to put 2 plus 3i over n to the 4th, because that's f of xi, times delta x, which is 3 over n. And overall, we can simplify this a little bit, because 3 over n is basically a constant. We can take this out, and then we can say, therefore, integral 2 to 5 x to the 4th dx could be calculated using 3 over n times limit n going to infinity of the Riemann sum I from 1 to n 2 plus 3i over n to the 4th. I'm not going to exactly calculate what that is, but if you were to calculate that limit, you're going to get the exact area that you want. And that's going to be all for this video.